Okay, everybody. In this section, we're going to be moving on into section 1.2, which is titled Row Reduction and Echelon Forms. The good thing is that in this section, we're not really going to learn anything new. We're going to kind of go back over some of the stuff we covered in the first video, but we're going to actually apply some names to some of the stuff we were doing so that we have a little bit more of a structured format as we move forward in the regular sections. So what I want to do is spend a few minutes talking about what is echelon and then also reduced echelon form. So a couple definitions here, and then I'll show you some examples in the next couple slides. So if a rectangular matrix is in echelon form, or as some books reference it as row echelon form, this will only be true if the following three properties are met. So let's go over these three properties here. Number one, all non-zero rows are above any rows of all zeros. That essentially means that if you have a row full of zeros and nothing else, it must go on the very bottom of your matrix. Number two, each leading entry in a row is in a column to the right of the leading entry of the row above it. This is similar from the last video when we were always focused on isolating like the one in the first position of the first row. And then when we moved down to row 2, we had to move over to the X2 column. That's kind of the same idea. As you work your way down, you have to make yourself move to the right to create your leading entry. And then finally, number 3, all entries below a leading entry in a column are zeros. Now, in the past video, I made you eliminate everything above and below the ones. Technically, for echelon form, you only have to make the numbers below the leading entry 0. So echelon form is kind of the basic form of what you can do. This will answer certain questions. The thing I usually suggest to my students is that when you are trying to answer a yes or no question in a problem, usually echelon form will suffice and you don't have to go any further. But there are going to be times that you have to go all the way to reduced echelon form or reduced row echelon form, as some books reference it. The only difference here is that there are 2 extra criteria that have to be met for you to be in reduced echelon form. The first one, or number 4 here, says the leading entry in each non-zero row needs to be the number 1. We're kind of already used to that from the past video, but officially that's not required in echelon. It's only required in reduced echelon. And then finally, number 5, each leading one is the only non-zero entry in its column. That goes back to my point a few minutes ago from point number 3. Instead of making just the numbers below the leading entry 0, you now have to make everything above and below the leading entries 1. The reason that we go a little bit further into reduced echelon form in this section is because if you are actually looking for the solution to something, like the question says, what is the answer to this? You have to go all the way to reduced echelon form in order to achieve that. So for those who are more of a visual learner, let me kind of show you some examples of what I'm talking about. So the following matrices you see at the top of your screen are in echelon form. The leading entries, or the black boxes I'm going to call them here, may have any non-zero value. The starred entries, which I'm using an asterisk here, may have any value including 0. So what you can see in these first 2 matrices is that, number 1, as you work your way down, the leading entries always move further to the right as you move down each row. Everything below those leading entries are zeros. So let me circle all these as well. All right. And then any rows of all zeros, which in this first matrix, there are 2 rows of all zeros, those are on the bottom. That's enough to suffice to echelon form of a matrix. Now, what you see is at the very bottom here, I took those exact same matrices and I converted them into reduced echelon to show you the difference. So first thing you'll notice in all of these is that the black boxes that I was calling the leading entries, in reduced echelon form, those now have to become the number 1s. That's required. The second thing that's new that I'll circle in green here is that the numbers above the leading entries are now all zeros versus in the top right one and the top left one, it was just the numbers below the leading entries. You'll notice that there still are some starred values even in reduced echelon form. Those starred entries can be any number, including the number 0, as we go through our echelon and reduced echelon form. All right, now that we know the difference between echelon and reduced echelon, there's two more definitions that we're going to need over the next few lectures. So when you do row operations on a matrix and you produce an echelon form, further row operations to obtain the reduced echelon form do not change the positions of the leading entries. So going back to my previous slide, when you go from echelon to reduced echelon, you'll notice that the black boxes just became ones. They don't move up and down once you get the leading entry location. It stays exactly right there. So our new definition is going to be a pivot position in a matrix A is a location in A that corresponds to a leading 1 in the reduced echelon form of A. So even though I put the echelon forms here and not the reduced echelon forms, remember, since these leading entries, we called them, don't move, we really have a new word for leading entry. A leading entry for us essentially means it's a pivot position. This is the point in each row / column that the numbers pivot, and that helps you solve certain aspects of the problem. The other thing, which we won't really need much today, we might do one example about it in this video, but later on, we're going to focus on some ideas that require you to use the pivot column, not just the pivot position. So a pivot column, and I'm going to highlight this because we're not going to use it very much right now, is a column of A that contains a pivot position. The reason that I stress that is because since it says a pivot column is a column of A, you have to go back to the original matrix A in order to find a pivot column. A pivot position can't be found until the echelon form. Once you find those, you have to go back to the original matrix to identify the pivot column in this case. All right. So that being said, in a few minutes, I think we're going to do an example talking about pivot columns. We'll look at how to find that when we need to. So like I said, there's not many problems in this section that we're going to work, but I am going to show you a few examples of kind of hammering the ideas we covered last time in the video, but using new names. So example 1 here says, row reduce the following augmented matrix to reduced echelon form. And so here's just a random matrix I made up. We want to put this into, like I said, reduced echelon form. So the first issue you're going to see, kind of like from the last video, is that we do not want a 0 in the upper left-hand portion. That's going to need to be a number, and in this case, more specifically, needs to be the number 1. The good news is that both positions below the 0 are already 1s, so you just need to interchange one row or the other. It doesn't really matter which one you interchange here. When I look at the problem, the first thing I see is I'm probably going to interchange row 1 and row 2. That's just my preference. So let's move row 2 up, and let's move row 1 down. Row 3 will leave exactly the same. All right, so we already have our leading entry of 1 done. Remember, everything below that and above it needs to become zeros, which one of them already is. We just need to get rid of that 1 in row 3. So going back to what we learned in the last video, we're going to take row 3 here, and we're going to subtract row 1. So row 1 and row 2 do not change. And if I take the values in row 3 and subtract the values in the top row, 1 minus 1 is 0, 3 minus 0 is 3, 0 minus negative 3 is also 3, and 1 minus a negative 1 is 2. So our first pivot position is done. If you look to the next column over, or I should say the next row down, your next pivot position should be in the next column over, hopefully, which it is. We move down to this 1, which is already the number that we want. We just need to make everything above it and below it 0. Above it's already done. We just need to change the 3 on the bottom. So we're going to pick on row 3 again. And in order to get rid of the 3 by using only the pivot position above it, I need to subtract 3 row 2s. So once again, the top 2 rows are going to remain unchanged for the time being. And if I take every value in row 3 and subtract 3 times the number above it, this is going to end up being 0, 3 minus 3 is 0, 3 plus 3 is 6, and 2 minus 0 is 2. All right, we've got our first 2 pivot positions done. And if we move down to the next row and shift over, you will notice that our next pivot position is a 6. Well, in order for this to be in reduced echelon form, we need to make sure that that becomes a 1, and then everything above it needs to be a 0. So in order to make that 6 a 1, I'm going to scale row 3, and I'm going to multiply it by a 6th. That's not going to make a very nice number at the very end, but at least it'll make the number we need to be a 1 a 1. All right, so once again, we're not touching row 1 and row 2 just yet. And the bottom row, if I multiply everything by a 6th, will be 1, and then 2 times a 6th is a 3rd. You now notice we're almost done here. We got all 3 of our pivot positions as the right number. Our last step is to make the 2 numbers above that last 1 a 0, and then we will be done. So we have to replace row 1 and row 2 with different things. For row 1, we're going to add 3 row 3s because -3 plus 3 would be 0. Row 2 is a little bit nicer here because all you have to do is take row 2 and add row 1. So this time, the only row we're not messing with is row 3. So good news, row 3 is done, it looks like. So if I were to take row 1 and add 3 row 3s, you would get 1, 0, -3 plus 3 is 0, and then -1 plus 3 times a 3rd would be -1 plus 1, which is also 0. That's nice. Not really necessary, but nice. Row 2, I'm just going to add the number that is, oh, and I wrote this wrong. I apologize. I just caught that. Let me erase this. I didn't mean R2 plus R1. I meant R2 plus R3. I'm sure some of y'all were looking at, oh, he messed up, he messed up. Well, thankfully I caught myself before I posted this video. So, excuse me, take the values of row 2 and add the numbers right below it. That should be 0, 1, 0, and then 0 plus a 3rd is a 3rd. So as you can verify, our 3 pivot positions are 1s. Everything above and below it is going to be a 0, and there is no row of all zeros to worry about. So if I were to erase those 3 red dots here, what you have just done is you have put the original matrix into reduced echelon form. That should look very familiar from the video if you've watched it on 1.1, but we now have a new name besides just solve a problem. We now know a name of what we're trying to do here. All right, so let's do a slightly different example. A little bit larger matrix, and usually when I give you a larger matrix, it means I'm going to kind of scale back on what you have to do. What I would like you to do on this one is I want you to row reduce this matrix to just echelon form, and then I want you to locate the pivot columns of matrix A. So remember that since we're only doing echelon form here, 2 things you don't have to worry about. Number 1, the pivot positions do not have to be 1s. They can if you want them to be. And then only the numbers below the pivot positions have to be 0s. Above the pivot positions can be any number that you would like. So when I look at this problem, even though it's not required to put a 1 in the top left, I think changing this 0 and this 1, which means interchanging row 1 and row 4, is our best first step here. So let's start with that. So I'm going to take row 1 and I'm going to interchange it with row 4. If anybody's wondering why I use the little weird arrows there, that's just the way my teacher back in the day taught me. It really doesn't matter what symbol you use. I use a little like kind of an upside down parabola thing. That's how I've always learned to interchange. Some people use different things, but to each his own. Anyways, so 1, 4, 5, -9, -7. Row 2 will remain the same. Row 3 will remain the same. And row 1 comes down to the bottom, which is 0, -3, -6, 4, 9. Now, even in echelon form, we've got our first pivot position. I still have to make everything below it a 0, even though the above's not going to matter in a minute. So that means I need to change row 2 and row 3 to make those zeros. So let's take row 2 and just add row 1 to it. And let's take row 3 and add 2 row 1s to it. So row 1 remains the same. Row 4 remains the same because that's already good enough for us. And so row 2, if I add the numbers right above it, you will have 0, 2, 4, -6, and -6. If I take row 3, double the top row and add it to it, you should get 0. -3 plus 8 is 5. 0 plus 10 is 10. 3 minus 18 is -15. And -1 minus 14 is -15. So none of these numbers look very pretty right now, but at least as I'm glancing, and I'm going to try to cram it over here on the right-hand side, while nothing I'm going to replace yet, we have a good pivot position. This 2 would be our next one. I think to make the math a little bit easier to get rid of the 5 and the -3 below it, I noticed that row 2 can be scaled and row 3 can be scaled because there's something in common with every number. So what I'm going to do is I'm going to take half of row 2 and a fifth of row 3, just because everything is divisible by those two numbers in those rows. And what happens is while your top row doesn't change, and I'm going to squeeze it in over here on the right, when I scale row 2 by a half, I get 0, 1, 2, -3, -3. And for row 3, you get 0, 1, 2, -3, -3. And that is actually a reason to talk about. For the first time, at least in the video and a half, we have two rows that are identical. Now, at this point in the video, you probably don't know what that means. And maybe you can kind of see what's going to happen. But after this next step, we're going to pause for a second and I'm going to talk about some shortcuts that we can start using after I've shown it once through. So for right now, I still have my same two pivot positions that I have found. I just need to make everything below that second pivot position a 0. So I'm going to take row 3 and subtract row 2. And I'm going to take row 4 and add 3 row 2s. So your top two rows are not going to change here. Your third row, if you take every number in row 3 and subtract the number right above it, you're going to notice that every single number should cancel and you get a row of all zeros. For the bottom row, you have to add 3 times row 2, so you should get 0, 0, 0. What is that? 4 minus 9, which is -5, and then 9 minus 9, which is 0. Well, that's nice. So at this point, we have our 3 pivot positions, 1, 1, and -5. So that part is done, because remember, they don't have to be 1s in echelon form. The only rule that we're not following currently is that since we got a row of all zeros, that has to be moved to the bottom. So there's not really much to do here except for we are going to interchange row 3 and row 4 here, which will give me the top row stays the same. The second row stays. Row 3 gets moved up, and row 3 gets moved down. And so I have just answered the first question. This is echelon form, just reminding you, those are our 3 pivot positions. Now, let me go ahead and finish the problem, then I'll come back to that shortcut I was talking about a few minutes ago. The last question says identify the pivot columns, and here's how we do that. As you can see in the last answer, I have the 3 pivot positions circled. You'll notice that the first one is in column 1, the second one is in column 2, and the third one is in column 4. What you have to do is you have to go back to the original matrix, and the 4 columns that make up from the final pivot positions represent the pivot columns. All right. So I believe on the homework, it's just going to tell you to identify the columns here. If you're wanting to get a little bit more specific, what we could do, and we'll talk more about this in the next video, that first column, the 0, -1, -2, 1. The second column, -3, -2, -3, 4. And the last column, 4, 3, 3, -9, those are your pivot columns because each column by itself will represent a pivot column. So while that finishes the problem here, let me go back to the shortcut I was talking about because we're going to use it a bunch in this class. If you look at the 1, 2, the third matrix, this one right here at the top right of your screen, you notice that row 2 and row 3 became exactly the same once we scaled some stuff. You also noticed on the next step that one of the rows that matched went to all zeros. So this is part 1 of the shortcut. If you ever get two rows that are identical to each other, the bottommost one automatically goes to all zeros. You don't have to do any work to show me that. It's an understood fact that that will always be the case. Even further than that, it's a little hard to see on this one, but if you look back one step, you'll notice that row 2 and row 3, at this point, some of y'all might notice that they are actually multiples of each other. If you multiply everything in row 2 by 5/2, you would get the elements in row 3. So my second shortcut to you that we will see occasionally is that if you ever end up with two rows that are not only equal to each other, but are multiples of each other for every single element, then you can make the bottommost row all zeros. Let me repeat that and pause the video and take the notes if you need to. If two rows are identical, the bottommost one goes to zeros, all zeros. Further than that, if every element of one row is a multiple in the other row, then the bottommost row goes to all zeros as well. So we're going to use that a lot. We may even use it again in this video. I don't remember, but take advantage of that rule when it comes up in the problems. All right, so the last thing I want to cover in this video, because there really isn't much new to talk about, is these rows of all zeros. What exactly does that mean when you get that? And that's what we're going to talk about for the last 15 or so minutes of this video. So the row reduction algorithm leads directly to an explicit description of the solution set of a linear system when the algorithm is applied to the augmented matrix of the system. So let's suppose, for example, that the augmented matrix of a linear system has been changed into the equivalent reduced echelon form. So all that first paragraph says is we did our row reduction and we are now here. That's as far as you are ever going to get in this particular problem. So what does it mean? If you were to write out exactly what each row means, the first row would mean x1 minus 5x3 is 1. The second row tells you that x2 plus x3 is 4. And the last row simply means 0 equals 0. In the last video, we saw the example where if you had 0 equals a different number, that was a false statement and thus formed an inconsistent solution. But as we know, 0 does equal 0. So what that tells you was the last little two sentences I have at the bottom of your screen right now. In this case, the variables x1 and x2 corresponding to pivot columns in the matrix are called basic variables. Now, this definition uses pivot columns for an example. This can easily be changed to the word positions and still holds. So if you'll look, x1 and x2, so the column that represents x1 and the column that represents x2 have pivot positions in them. So what we can call those two variables are actually basic variables, which means you are able to solve for them. The one variable that you don't circle, so let's see, in blue here, x3 does not have a pivot position anywhere. All right, -5 and 1. Then when you go down the next row, there is no pivot position in column 3. So therefore, that variable we call a free variable, which in linear algebra means this variable can be anything. So going forward, if you can let x3 be any value you want to be, therefore it is infinitely many solutions understood. If you go back to the last video, we said there's either one solution, which we've seen, there are no solutions, which we've seen, and we're starting to see the idea behind infinitely many solutions becoming more popular. All right. So what I want to show you here is here's a problem that I've kind of already reduced most of the way for you, but I want you to find the general solution of the linear system whose augmented matrix is this. So since it says find the general solution, I want to try to identify the pivot positions because we're going to have to eventually put this into reduced echelon form. So let's see. There's a pivot position. There's a pivot position. And here's a pivot position. The row of all zeros is on the bottom, so you're good to go there. The only issue we have with this not being reduced echelon form is you cannot have that -8 right there because everything above and below the pivot positions must be 0. So the only step you have to do here is in order to get rid of that -8, I'm going to take row 1 and I'm going to add 8 row 3s to that. So by doing that, you should get 1, 0, -5, 0, 0, and then 3 plus 0 is 3. We're not going to actually mess with any of the other rows in this problem. Just give me a second to get them all down here. That's the hardest part, or longest part. You now have a reduced echelon matrix. So now, in order to find the general solution, what you want to do is, because you can't go any further with this, is you want to write out exactly what it is you just found. So row 1 tells us that x1, minus 5x3 is equal to 3. Remember, the last column is the coefficient, or constant, not the coefficients. Row 2 tells us that x2 plus 4x3 minus x4 is equal to 6. Row 3 actually just tells us that x5 is 0. And then if I go back to my circled pivot positions at the top, remember, any column that you did not circle a pivot position in, which in this case is x3 and x4, those are your free variables. So you actually have 2 coefficients here that you can let be any number that you want to be. Now, what I did not show you on the last slide is you are not done. From this step, and I'm going to write a little note right here above it, you have to solve for the basic variable. So in each of these equations, you need to get the basic variable by itself. So in that first column there, or first equation, x1 is my basic variable based on what I have circled at the top. So if I were to do some algebra and get x1 by itself, this would be 3 plus 5x3. In the second equation, x2 is your basic variable. So if you move everything over, you'll get 6 minus 4x3 plus x4. In the third equation, there's nothing you can do. That just says x5 is 0. And then your last statement says x3 and x4 are free, which for right now, that is your general solution of the system of equations. So kind of thinking out loud of what this is going to tell us going forward, this simply says, let x3 and x4 be any number that you want them to be. And based on the numbers you pick, if you plug those into the respective spots in the previous equations, you will get one of the infinitely many solutions of the original linear system. Now, is this the best way to write our answer? Absolutely not. Over the next couple of videos, we will learn better ways to express our answer of infinitely many solutions. That's just not meant for this section as of this time. All right, and then to wrap up our video on 1.2 is let's do another critical thinking question. We saw one of these at the end of the first video. I like to throw a few of these in chapter 1 to get you thinking to end this section. Example 4 says, can you choose H and K such that the following 3 situations can happen? Now this is 3 different answers. Keep that in mind. I want you to pick an H and K that will force the system to have a no solution. I want you to pick an H and K that forces the system to have exactly one solution. And then finally, I want you to pick H and K such that you will force the system to have infinitely many solutions. To do any of those, you have to take your matrix and reduce it as far as you can. So I'm going to start off by writing our augmented matrix. So this should be 1, -3, 1, and then 2HK. If you need a refresher on how to write an augmented matrix, go back to the first video and look over that lecture. So to put this in the most reduced form I can, the first thing I want to do is I already have the 1 in the right position. I want to get rid of the 2 that's right below it. So I'm going to take row 2 and subtract 2 row 1s. So that will be 1, -3, 1. And then for row 2, that's going to be 0. That actually becomes H plus 6, and then K minus 2. And since we don't know what H and K are, we have to force them to be something. That's as far as you're going to make it. So now let's see if we can answer each question. So beginning with no solution, or part A, we talked about in the last video that the only time you will see no solution is if you can force the pivot position first has to be 0. So that next pivot position down, the H plus 6 must equal 0, guaranteed. So if you solve that, we know immediately that H must be -6. But not only that, it must be 0, but as we've now seen, the K minus 2 right next to it cannot be 0. Because if they're both 0, that's the answer for infinitely many solutions, and that's part C's answer. For it to be no solution, you need the K minus 2 to be anything other than 0. So if you solve that, we can see that K cannot be 2. So for part A of this problem, if you want to force a no solution answer, you need to force H to be -6 and K cannot be 2. Speaking of that, even though I'm supposed to go in ABC order, I'm actually going to go ahead and jump to part C because that's the one we just talked about as well. For it to be infinitely many solutions, the H plus 6 and the K minus 2, we need a row of all zeros for this to happen. All right. So not only does H plus 6 need to be 0, which we've already seen that H needs to be -6, we need to force the K minus 2 to be 0, so thus K needs to be 2. Those are the only 2 pair of numbers that will force this system to have infinitely many solutions. So that's the answer to part C. For part B, different kind of thinking. Let's go back and answer exactly one solution. So for exactly one solution, it's kind of the opposite of what A and C have been. If you want to have exactly one solution, this number, the H plus 6, cannot be 0 because we have to force there to be a pivot position there. So a pivot position can be any number other than 0. So the first thing I know is that H plus 6 cannot be 0. So thus H cannot be -6. And so now thinking out loud, if that circle is not 0, it does not matter what is in the K position. Because if there is a pivot position there, then any number you get in the far right column will be the only solution for, in this case, x2. So there's actually no stipulation. K minus 2 could be 0. k minus 2 could be not 0. In the end, we can let k be any value. And how you'll see it written on your homework is they will write it as k needs to be a real value. So if you've never seen this mathematical notation, this little inscribe right here, this is the mathematical symbol for in or enclosed in. K needs to be enclosed in, and this is called a double R notation. This is talking about the real space. So any real number would suffice to this particular answer. So part A and C, no solution, infinitely many are very similar with one's adjustment. Exactly one, that's the ones where you need pivot positions that represent every variable. So that officially ends section 1.2's video. In the next video, we will introduce how matrices and vectors go hand in hand and start to make the connection of where linear algebra, and then as a lot of y'all have already had or will have, where calculus start meeting each other.